we start from the last statement in the last lecture, because we did not complete the proof of Cauchy Tetrahedron argument. So, if you remember, we have chosen a E1, E2, E3 orthonormal basis, and we have chosen 3 points on each of these axes. The triangle formed with these 3 points, we considered the plane of this triangle, and we considered the normal to this plane. Then, calling epsilon, so we keep fixed this normal, we call epsilon the distance between the origin of this orthonormal system of coordinates and the plane of the triangle. Of course, when you change epsilon, you get a smaller, if epsilon decreases, a smaller tetrahedron, or if epsilon increases, a larger tetrahedron. If you keep the 3 other faces given, the 3 other faces of this tetrahedron are the 3 triangles which are formed with 2 of the 2 points which are on the 2 axes we have selected, and the origin. So we have actually a family of tetrahedrons T epsilon, characterized by the same normal n. Then you have the face f n epsilon, which is the triangle having normal n. Then you have the faces f I epsilon, which are the faces formed by the origin and 2 arbitrarily chosen of the 3 points we have chosen. Remark that I call Fi epsilon the face whose normal is Ei, for having a compact notation. Okay? Now, the clever idea, it is difficult to say who had this idea first. The clever idea is to consider balance laws for a family of shrinking sub-bodies of a given body. It is not clear, again, this is another subject, is a subject of another science, rather sociology or psychology of science. Why this rather sophisticated mathematical argument is considered practical, and instead integration by parts is considered mathematical. Because nobody has practically seen a family of vanishing sub-bodies. There are also physicists who claim that all this is meaningless, because when epsilon is small enough, inside your tetrahedron you have 1 atom. And so all this argument is meaningless. Of course, you have to consider that this is a mathematical argument, in a sense which I will make clear later. Okay, so what we will need is a formula which comes from Euclidean geometry, the area of Fi epsilon is equal to the area of Fn epsilon times the inner product N and EI. The inner product between two unit vectors is the cosine of the angle formed by the directions of these two vectors. And this formula is simply the formula of projections, orthogonal projections of areas, which is a crucial topic in optics, and it was deeply studied already in Hellenistic geometry. Okay, so maybe the reason of the success of this argument is based on the fact that the mathematics used is more ancient. This is a possibility. Okay. Now, we postulate balance of force on the generic T epsilon tetrahedron. So, using a point of view which is with which I disagree rather completely, we can decide that the basic postulate, one of the basic postulates of mechanics, is balance of force. This argument is true, as we already mentioned in the previous lecture, for every integral balance law. So the existence of flux and linearity of flux with respect to the normal of the surface you are considering in your continuum, this argument is independent on the particular nature of the physical quantity you are balancing. Okay. But for fixing the ideas, then we will discover that we don't use the particular structure of balance of force, so the argument is more general. So we write integral over T epsilon of the source of force. Here you include also the kinetic energy, the inertia forces. What is important is that this quantity is obtained by means of a volume integral. So in the language of measure theory, you have a density which is absolutely continuous with respect to Lebesgue measure. So when you have a volume 0, this quantity is vanishing. Okay? So source of force is something which is vanishing when the considered body has volume 0. Then you add integral over the phase Fin of the force per unit area applied by the body on the side N plus. So the part of the body which is on the side of your triangle where the normal N is pointing on your body, because the convention used by Cauchy is that when you have a normal N, the vector Tn, so-called Cauchy vector, is a field, a vector field, because in different points of the surface it has different values. Okay, it is a field which is representing the force per unit area applied by the body on the side N plus on the body of the side N minus. Then, sorry, this was Fn epsilon. Then you have sum I1 to 3 of integral of Fi epsilon t minus Ei. Okay? And the sum of everything is 0. Now, remember that the normal of the face Fi is Ei, but the outer pointing normal is minus Ei, and because of the convention we have introduced, the vector t minus Ei is the force which the outer part of the body with respect to the tetrahedron is applying to the tetrahedron. Okay? So this quantity has to be 0. Okay. Now we are quickly resuming what we said in the whole lecture, last lecture. Then the idea is to apply when epsilon tends to 0 the mean value theorem for integrals, because the hope is the following. This is the idea of Cauchy. This volume is tending to 0 with epsilon cube. This area, the area of this triangle, is going to 0 with epsilon, and the same for each of these areas, as this formula is telling us. Okay, so I don't need to remind by heart the formula for the volume of a tetrahedron, because next step is to divide everything for times 1 over epsilon square and calculate the limit for epsilon which tends to 0. So this is a purely mathematical argument, because as this is going to 0 with epsilon cube divided epsilon, this animal tends to 0, while this animal and that animal are non-vanishing because the limit is finite. So we already start to see how this balance can give us an information about Tn in terms of T minus Ei. And this is the bulk of the idea of Cauchy. Okay? But as I told you in the last lecture, and as Cauchy knew very well, and this point is very important, because you have to understand why the variational principles are more powerful. This equality is a vectorial equality. B is a vector. T, the integral of B is a vector. T is a vector. T minus Ei is a vector. So you cannot apply mean value theorem. Even if this is not very well known, and there are many textbooks in which the mean value theorem is applied, and I have seen very much cited papers in which the mean value theorem is applied for vector fields. There is a trivial counterexample which tells us that you have to be careful. And for solving the technical problem behind the impossibility of applying the mean value problem, behind this, power is popping up again. And so you discover that the most fundamental concept in mechanics is not force. The most fundamental concept in mechanics, it is power. So even if you try to keep the word outside, and Cauchy postulation is based on the effort of avoiding to use the power, the concept of power as a basic one, then without knowing, without telling maybe explicitly, this concept comes out. So I first remember, yeah.
But then you can still do it component-wise.
Which means
doing something as a projection, so it's a work in a sense, but I don't want for people.
Okay, you ruined my theatrical way of exposing. Yes, actually, this is the standard trick, but I show you. Okay. Yeah, I know that you study it.
Yes. For a long time.
So, but this counterexample maybe you have not seen, or you have seen it. Right?
I don't know.
So if you call this E1 and E2, okay, and if you define in the lower side of the triangle an arrow parallel to E1 whose length is exactly equal to the distance of the application point to the diagonal. And if you do the same, but along E2 in the upper triangle, okay, and you call the obtained vector field V, it is clear that the vector field V is continuous. It is continuous because it tends to the vector 0 on the diagonal. Okay? However, the integral of V is clearly parallel to E1 plus E2. Okay? And the mean value problem, theorem cannot hold, because you will never get a value of V parallel to E1 plus E2. So there are two ways for solving this. The introduction of explicit introduction of power, or the trick, which is equivalent, which was mentioned by Carlo before. Because actually, if this balance is true, then for every V0, this equality is true also. To state that this equality is true for every V0 is equivalent to assume that the vectorial quantity is vanishing. Okay, so in particular, if you consider V0 parallel to E1, E2, and E3, you get the three components of this quantity. But this trick, correct one, is hiding the fact that you are imagining a virtual displacement of your tetrahedron, which is a rigid one. Indeed, following the tradition of Piola, for a reason which I could not understand for a lot of time, in the Italian books, in the good ones, you find they call this integral equal to 0, they call it balance for translations. And the balance of angular momentum, they call it balance for rotations. And everybody we will talk about this quickly. Everybody who has seen how painful it is to postulate the balance of angular momentum and then deduce that the tensor, the Cauchy stress tensor, is symmetric, we'll see that with few lines of calculations, considering the rigid body rotation, you get very elegantly the same result. Okay, now, with this trick, you can introduce V0 inside the integral. By the way, I'm not indicating the volume, the area, because when I tell you the domain of integration, when it is not indicated, I'm using the appropriate dimensional measure. Okay, so I can divide everything times 1 over epsilon square, okay, and then I can calculate the limit for epsilon which tends to 0 of this quantity. So what we are doing, we are considering the virtual power expended on a translation of your tetrahedron when this tetrahedron is subjected to a virtual displacement. Indeed, both Lagrange and Piola call this the principle of virtual velocities, not the principle of virtual powers. It's a different way for meaning exactly the same thing. Now, you can apply here the mean value theorem. So you can say that this integral is equal to epsilon cube times a coefficient k, which gives you the volume of the tetrahedron, times b calculated somewhere psi belonging, let's call it psi bar, belonging to the tetrahedron T epsilon n dot V0. Okay? Epsilon cube, of course. Okay? So, K epsilon cube is the volume of the tetrahedron, and this is the integrand scalar calculated in 1 point. Okay? Okay. Now, similarly, this integral is equal to the area of f n epsilon times what? T n in a point psi n, inner product V0. Now stop here for considering once more the beautiful properties of a tetrahedron. A tetrahedron has faces which are planar. So the normal is the same in every point. So this n does not depend on the point where you are calculating t, and does not depend on the epsilon, the n. If you want to be very careful, you have to call psi epsilon. Psi epsilon. Okay? Because when epsilon is varying, the point where you are estimating the field is varying. But psi epsilon n belongs to the phase f n epsilon. Okay? And finally, you can write here the area of f n I t minus ei in psi epsilon I dot v0, and this animal belongs to the phase f n I. Okay? Now all this is Cauchy mathematics. This is done with the order and the rigor typical of Cauchy demonstrations, which are the basis of modern analysis. Okay. Now, this limit is 0. And I will not bore you recalling that the sum of limits is the limit of sums. Okay? By the way, consider that Cauchy, while developing this argument, was at the same time developing these theorems. Okay. So we try to rewrite in a more clean way this formula. So we have limit epsilon tending to 0 of 1 over epsilon square bracket f n epsilon t n psi epsilon n dot v0 plus sum f n I t minus ei psi I epsilon dot v0. I was a little bit wrong in choosing the space because I need to replace this inside and I've not left a lot of space, but we can work out this. So plus sum, and here I can replace n dot ei area of f n epsilon. Look how elegant is what we are doing. Again, we will not calculate the area of f n epsilon because we know that it is a constant times epsilon square. So if I factorize f n epsilon, area, this is a constant, different from 0. Okay? So this limit is equal to 0 if and only if this limit is equal to 0. But v0 is arbitrary. We can factorize it. And in general, it is non-vanishing. So you get the vectorial quantity, the vectorial equality, this one, in an elegant way. Maybe if you go to read one of the books you have used in which this proof is written. There is a very high probability that the final formula, which is true, is obtained with false deductions. You know, ex absurdo omnia secuntur. So also true things can be proven with false arguments. What is delicate is that you need to use correct deductions if you want to be sure of your result. Okay, if you already know the result, then you can, waving your hands, trying to persuade people that the proof is easy. Okay, we stop here for doing another delicate consideration. Another assumption by Cauchy is that these vector fields are continuous. So another assumption is the following. If you consider a Cauchy cut with normal n, and if you translate it, the surface, keeping the normal constant a little bit, then the Cauchy vector is changing a little bit. So this limit can be calculated, and it is exactly Tn in the point P, which was the origin of our axis, plus summation I from 1 to 3 of n dot ei t minus ei in the point P, which is a wonderful relationship, not yet what we are looking for, but this is a wonderful relationship between the Cauchy vector Tn in the point P, so the force per unit area estimated through a surface whose normal is n, in terms of the same quantities estimated along the three orthonormal vectors which we have chosen in our basis for characterizing our reference. Now, the crucial point here is the following. The crucial point is that you have minus sum I from 1 to 3 n dot ei t minus ei p So the theorem is not yet completed. We need to prove what is called Cauchy lemma. This was a very interesting thing which happened to me. By the way, the tradition in Italy is that in every course of strength of materials, this theorem has to be proven. When I prepared my concorso for becoming associate professor, in the list of possible arguments, this one, and in every book of strength of materials, this argument is presented in a more or less rigorous way. So I was really astonished when I tried. Of course I cannot draw very well, so you have to imagine. So imagine to have a sphere, a disk in the plane E1, E2, and to translate it along E3. okay? And you translate it of a measure which is epsilon square, okay? So you have the top of the pill and the bottom of the pill. The radius of the sphere is, of the disk is epsilon, okay? So you have this family of p epsilon volumes, which are cylinders, very thin cylinders, okay? You can apply the integral balance with a translation, of course, which we have written before, also to this animal. However, as epsilon is going, the height of the cylinder is epsilon square, the lateral mantle of this cylinder has an area which is proportional to the perimeter of the disk times epsilon square. Okay, so it goes with epsilon cube. While the top and bottom disks, they have an area which goes with epsilon square. So when epsilon tends to 0, what you get? You get T minus EI plus minus plus TEI equal 0, sorry, it has to be this way, okay? Because this animal comes from the integral of the top, this animal comes from the integral of the bottom.
I3 maybe, with reference to the...
Yeah, I3, but you can repeat it. You can repeat for E1 and E2, okay? So this is exactly the same calculations I did before. And so at the end, what you get is this equality, which was interpreted as the action-reaction principle for contact forces. So the force which side plus is exerting on side minus is minus the force which side minus is exerting on side plus. Okay. Again, this is obtained using the principle of virtual powers for a generic translation of this new family of sub-bodies of the given bodies. Which means that this minus and that minus simplify, okay? And if you have studied something about linear algebra, this is the proof that the dependence of T with respect to n is linear. Because linear dependence is this one, Tn equal T summation over I of alpha I n I EI equal summation over I alpha I T EI, which is written here, if you remember that n dot EI are the components of n in the basis EI. So now we can discuss the point which I wanted to underline when I decided to talk about this theorem to you. I didn't want to show only the series of weak points and the nature, the deeply mathematical nature of an argument which is considered more physical simply because people are more accustomed to it. But, to my knowledge, it is a merit due to Cauchy, it is a contribution, main contribution due to Cauchy, the fact that he introduced the first physical quantity which is not a scalar, which is not a vector. This I have checked carefully. Stress a la Cauchy, the linear map which maps to every n the force per unit area applied to a surface having normal n, this physical quantity has been introduced between 1823 and 1825, while green deformation measure was introduced later than 1860. So, we have this is a long story which has been told you, I hope, in the lectures of Physics 1 and Physics 2nd year. They came to us and they tell, there are some quantities which we call scalar. Example, mass, okay, which are independent of the observer. They specify some physical properties of the systems you are considering, and one real number is enough for describing them. Then they start talking about velocity, displacement, force, and this is very dangerous because displacement is a vector, velocity is a vector, force is a covector. But as we have an inner product, we can mix them. So they talk about velocity and they tell you, attention, there are some physical quantities which are varying with a change of observer in a different way. By the way, velocity, we have seen, is not varying as a vector with a change of observer if one observer is in a relative motion with respect to the other one. Here we have a new physical quantity. You have to think about this. When you have a deformable body in a referential configuration, you have to think that in every point you have nailed a linear map. So you have a tensor field. By the way, I have said, I think to more than 100 scientists, that the word tensor used by mathematicians for linear maps from a vector space to another one comes from Cauchy and the concept of tensio, stress, and nobody knew. The reason for which a linear map between a vector space and another one is called tensor is because the first occurrence in physics, of a linear map which describes a physical quantity, this first occurrence was Cauchy stress. So the way in which inside a body one part of the body is acting on the other part. So in every point you must imagine a vector n which is varying on the sphere of radius 1. For every n, you have a vector Tn, which is expressing the force per unit area, which is exerted by the side plus on the side minus of this body. Okay? Well, when you change n, you change Tn. So to know that this map is a linear map allows you to introduce here a quantity which we can call Cauchy stress, T, which is the linear map between n and Tn. If you have chosen a basis, you can represent this linear map with a matrix. As we will discuss quickly that T is symmetric, we already mentioned it, then we know that there are 6 independent coefficients of this matrix. So when you change n, you change the force per unit area. Now, how T plays a crucial role in all applications is given by, for instance, the famous Tresca criterion of rupture, which in general is studied everywhere. If you have the normal n, and if you have Tn, the force per unit area applied in that point, you call shear component of Tn the projection of Tn in the orthogonal plane to n, and traction or compression the component of Tn along n. Consider that for fluids, Euler fluids, we have already seen that you don't have shear, you have only compression. In an Euler fluid you cannot have tractions. Okay, now there are some bodies, crystal bodies, fragile crystal bodies, which suffer very much shear. So if they see a shear stress lower than a given threshold, so if you have this is shear, okay? So this is a matrix. You saturate with one index, you get a vector. You saturate again, you get a scalar. This is the traction or pressure component of T in the direction n. So if you subtract to the vector Tn this component, you get the shear component. Now look, we have reduced to a problem of linear algebra. Given a stress tensor T, find when there exists a n such that this quantity is exceeding a given threshold. This is so-called Tresca rupture criterion. which is valid for some materials, not for all. Now, the fact that you have discovered that the Cauchy vector is a linear function of n allows you to treat the Tresca criterion in an algebraic way. Of course, in many books there is only the final result of this analysis. Anyway, you have to find, I tell you the recipe, you find the eigenvalues of T. As T is symmetric, there are 3, which may be equal or distinct. Then you calculate the maximum of the difference of the 3 eigenvalues of T. Okay? This maximum gives you the maximum shear which is exerted in that point. So the recipe for verifying Tresca criterion is the following. Find the eigenvalues of stress, calculate the maximum of the difference, and verify that everywhere in the body this difference is never exceeding your given threshold. Okay, so this is only one possible example of the importance of this result. But what is important is that instead of having infinite vectors to be specified to know the state of stress in a deformable body, this is the reason of the success of this argument. You have infinite vectors, Tn. For every n, you have Tn. So in order to specify stress in a given point, you need to know infinite vectors. So it is a hopeless effort to know everything about stress in a body if you are left only with this definition. The clever result by Cauchy gives us the possibility of determining all these infinite vectors in terms of 6 scalars, which are the 6 strict components of stress. So in a sense, this result is the beginning of modern elasticity, at least of modern elasticity. Okay. Now, okay, I promised, but of course we simply start now discussing about this. I promised to talk about constitutive equations and symmetry groups for deformable bodies. And I want to underline once more that if you decide to use the approach of Cauchy, you are in serious troubles. Instead, if you like energy, your life is much simpler. This animal is a tensor. So you have a tensor quantity which is a function of another tensor quantity. Do you know how many indices you need for representing the linear, so the simplest dependence? You have T, I, J, which is a function of f, h, k. For the moment, I'm not distinguishing between Lagrangian and Eulerian indices, which will make the story even more complicated. So this is equal to C I J H K F K H summation over H and K. So we are meeting for the first time the fourth order elasticity tensor in a very strange form because it is in terms of F. So. But my point is that I want to underline that I have a vector space, the space of tensors. I have another vector space, the space of deformations, and in order to establish the simplest relationship between these two vector spaces, I need a linear map between these vector spaces, which is a fourth order tensor. So talking about symmetry means to control what happens when I change the bases and I have four indices which are changing, which is in principle very difficult. On the other hand, if you have the energy, it is a scalar. The poor boy is very well behaving. You change the observer, you change the basis, and it remains the same. So, which is, in a sense, there is no simplest rule of variance than this one. Okay. If you remember well, we introduced Piola stress, calculating the derivative of W with respect to F. Okay, so what we are understanding with these simple reasonings is that the most natural quantity to be considered for invariance properties or for material symmetries is the deformation energy. Once we have characterized this quantity and its properties of invariance, then we will get for free the properties for stress. Of course, somebody could start claiming that then Stokes-Navier stress cannot be considered in this perspective, which is absolutely not true. Why? We will see that the dissipated energy in a motion with velocity v, this is the Eulerian integral of Navier dissipation stress, is this expression. Okay, you can replace inside T the constitutive equation in terms of grad V, and what you get is the rate of dissipated energy. So, when you want to study dissipation, you introduce the constitutive equation for dissipated energy and you impose its invariance. The dissipated energy cannot depend on the observer. So we will see that the argument which we need to find the two Lamé coefficients, which are the elasticity coefficients for isotropic materials, is the same mathematical argument which can be used to find the most general dissipation for Stokes-Navier materials. So actually, when you are studying a physical phenomenon, you have always an energy behind, a kind of energy, dissipated, stored, elastic. You study your properties in terms of this energy, and then you get, as a byproduct, the searched properties on the associated tensors. Okay, of course I'm talking maybe too quickly, but I will go in details for this. But what is very difficult to understand, now we go back to the double indices, is that objectivity is telling to you something concerning this index I. Material symmetry is telling to you something talking about this capital index. If you have a vector capital V, you apply F, you get F capital V. Okay, so this animal has components I equal F I capital A, V capital A. This is the deformation of the material vector V when passing from the Lagrangian to the Eulerian coordinates, to the Eulerian description, configuration. If you change the observer, you take this vector, let's call it small v, and you rotate it with q. So the rotation which is associated to a change of observer is a rotation I, j, small indices. They are changing the components of V. Using the notation of Levi-Civita, it is better to introduce the index J prime for telling that this is the index in another basis of the same vector space. So Vj prime, you must read in this way. The letter tells you the name of the vector you are considering. The index I is telling you the components of the vector V in the basis without prime. J prime is telling you the components of V, the same vector, in the basis EG prime. So this is the most efficient, correct notation. This gives you the new components of the same vector when you have changed the basis. Okay? Now, objectivity is talking about the small index. And we have already ruled, now we will prove that it is the only possible way, but we have already ruled away this Q. Why? Because when we have introduced the deformation measure CAB, F transposed F. This animal is a map, linear map, from Lagrangian vector to Lagrangian vector. If you change the components following a rotation, here you have this animal, but this animal is equal to okay? And when you saturate J primo, J, J primo, J, no, allora che ho fatto là? FI, sì, l'ho storzellato. Allora, qua ci vuole I primo, J primo, ecco qua. This is an automatic check of the mistake, because I need I prime, J prime, J prime. And because of orthogonality of Q, this quantity is the identity. So this animal, by construction, is independent of the observer. Okay? So it is built in such a way that when you change these indices in this way, the final result is not changed. This gives you CAB as the good candidate for representing deformation energy instead of F, in the sense that the dependence has to be on F, but the only dependence which is invariant under change of observer is a dependence on F via C. Okay? Okay, now we can conclude this lecture understanding what happens if I take a matrix U and I change in this way the deformation energy F, the deformation matrix F. So what I'm doing, instead of changing the index I, I'm now changing the capital index. So in a sense, of course there are some integrability conditions, but locally this is always possible. What happens is the following thing. I have a system of coordinates in the Lagrangian reference. Now I change these coordinates. So instead of using these coordinates, I use other coordinates. So I change this index in the deformation measure.
But now you are using a different convention on the name of the indices. Why don't you put the tildes on the B, for instance?
Yes.
I mean,
You are right, but for a reason. But you are right. No, it's of tradition. I don't know why I'm a victim of the tradition. So you are right. You are the cause of another change of my notation. Because we are changing the Lagrangian coordinates. And this is inducing a change of the deformation gradient. This animal, you can call as D. If the new coordinates are b x, capital X, b tilde, this matrix is trivially giving you this matrix here. Okay. So instead of using one system of coordinates, you are using another one. Locally, this is equivalent to introduce a matrix, a tensor on the left F. So it is not affected by the saturation over I, this animal. So while multiplying on the right side times Q is keeping C unchanged, changing the reference in the Lagrangian system is changing the C. So you have W of U transposed CU, and you have W of C. So you can consider the energy, because you can think your final deformation F as obtained in two steps. You first deform the Lagrangian, so you introduce a fictitious intermediate step of deformation, and then you apply the old deformation. And you can ask if this intermediate step added to C is changing or how it is affecting the deformation energy.
Okay, but now this use is a rather strange object.
Non-singular with determinant positive. This is the
only constraint you have.
Yeah, you are changing the coordinates in the Lagrangian whatsoever. Okay?
Because you do not have any notion of matrix no, not that.
No, you have, but you allow your body to undergo any intermediate deformation. You want to investigate all possible material symmetries. Okay? Now, you say that your energy W as the U matrix as a member of its symmetry group if this is equal to that. Which means either you deform your body with F or you deform your body with F tilde, the deformation energy is the same.
And of course it is a group because you can compose the use.
It is a group because you can compose, we will see in detail, but this structure tells you it is a group. Okay, now the crucial problem is the following. How many symmetry groups exist? And given a symmetry group, which are the deformation energies which are invariant under that symmetry group? This is a subject of algebra. Now, you need some differential geometry if you want. You have to study Lie groups, but I mean, it is not essential. You may ignore There is a common point with theoretical physics. There is sure lemma, because actually in quantum mechanics they have some energies which must be symmetric under some fields. So the theories are overlapping in a sense. Okay, this theory is very simple and very complicated at the same time. It is simple because conceptually you will discover there is not much more than what I said now. But technicalities are difficult. Before tensor calculus, the French geometers quarreled more than 5 years because there was a party which said that Lamé moduli were 1, and another party which said that Lamé moduli were 2. So it was not so simple to prove which is the symmetry group of isotropic materials. By the way, what is an isotropic material? The one for which this equality is true for every u belonging to orthogonal. So if you rotate in a rigid way your Lagrangian coordinates, you get the same deformation energy. Consider this is a local. There is a very misleading point here. Of course, if you are rotating only this animal here and the others are kept fixed, first you have a compatibility, kinematic compatibility. Second, you are deforming your animal. Okay? So what you have to think is that you change the variables in such a way that in one point you have this relationship. And then you estimate the deformation energy in that point. So it is a strongly local concept. So you are talking about the infinitesimal cube, the epsilon Cauchy cube, in the neighborhood of one point, and you are estimating its deformation energy. So this is another crucial point we will need to discuss. Why I tell you this? All the theory is useless and is being reformulated now if you have gradients of higher order there. So I am working to give value to the result of a young scientist in Paris who is working nearly full-time in characterizing the symmetry groups for second gradient materials. I mean, the importance and difficulty of the work is underestimated, so this work has to be defended, protected, and spread. So the name is Nicolas Offray. He works in this. Okay, so that's it for today.